to derive the velocity for a transverse wave, the equation of the velocity with the first method. So suppose we have a string here that is tense, so in equilibrium has the tension F for tension. I'm neglecting the mass per se of the string. Let's say I put now a force here, let us this. So I'm applying a force just on the y direction, and you will see that in some time interval I will have something like this. You know, this is the part that is already moving, and this part is still without motion. So here I put the force F on this y direction, this F sub y. Here I have the tension, the component. The F, that is the tension, is the x component of the total force if you want. For example, something like this. Oops. Let me do it more like this. Next point. The particles here are moving just on the y direction. So this is v sub y, etc. So they're moving with constant velocity. The impulse, I have the transverse impulse is f sub y times the time. And remember that this needs to be equal to the change in momentum. But what is the change in momentum? The velocity is constant. V sub y is constant. So now the change in momentum, that is the impulse is increasing because the time is increasing. But what makes that the change in momentum increases as the time goes by? This would be just the mass. So I have the change in mass. So that is because let me call this point P the point of division from the moving part and the non-moving part. So here the part that is moving is increasing. The portion of the string that is moving is increasing, so the total mass is increasing. Now the total mass, let me call it mu. Mu is just the mass per unit of length. So the mass would be mu times the length. Mass would be mu times the length. So now, what is the total change in momentum? What I need to know the length. So at time t, I have this point. I have that the particles are moving on the y direction to a velocity of this y that is constant, and I have b that is the velocity of the wave, and because this is the velocity of the wave, that means that the point P is moving at a constant speed of b. Alright, now, so at time t, the point P has advanced this distance. This distance is time times velocity. So this is how much P had advanced on the time, and what distance the particles moved on the y direction is also time, both times v sub y. So this is t v sub y. So first, the change in momentum. First, the mass would be mu, that is the mass per unit of length, times the length, the distance that v had advanced. So v times t. So the change in momentum on the transverse momentum would be here I have the v sub y times the change in mass, that is mu v t. Now this is the transverse impulse. So let me now talk about the transverse impulse. If you see, these are the same angle, so I have that the proportion F sub y divided by F that the tension is the x component of the force, is equal to the distance, always proportional to the distance on y divided by the distance on x. So t v sub y divided by t sub v. So I can cancel the t's, and if I want to solve for f sub y, have f sub y is equal to v sub y divided by v times f. Now, just in order you to see this, the magnitude of the force, remember, is the square root of the square of the components. So f sub y squared plus f squared. Now this is constant because the tension is constant. So I have no movement on the x direction. So I just have f squared. So this is the magnitude of the force, and if you see, this is a little bit greater than the tension at the equilibrium. So that means that as time goes by, after I did this, after I applied the force, I have that the tension of the string is increasing. So the tension increases a little bit, and the mass is increasing because more particles are coming into motion, and the change in mass is the one that produces the change in momentum because the velocity y is constant. So these particles have a constant velocity, not acceleration, but constant velocity. So I have here f sub y. Now I want the transverse impulse. The transverse impulse is I multiply everything by t, and now by the impulse momentum theorem, let me apply it to this motion of the string particles. So I have f sub y t is f v sub y divided by v times t is equal to the change in momentum, v sub y mu v t. And now let's find the velocity. So first I can cancel here the v sub y's as well as the time. So I have f is equal to the mass per unit length times the square of the velocity. So I have that the velocity is equal to the square root of the force divided by the mass per unit length, and this is the formula of the velocity for a transverse wave. So here we have a mass per unit length is mass. In a sense, you can consider it as proportional to density, and here I have force proportional to pressure to elasticity. So we will talk about this in other stuff, as Dr. Miller says, and now we have derived the velocity formula for the transverse wave, and if you see, this does not depend on the velocity of y of the particles, on the amplitude, on the frequency. It does not depend on anything, neither of the time. It just depends on the original tension of the string and the mass per unit length.